Hello students, so we are going to continue in this video on Brownian motion. So this is now better theory of Brownian motion than your Einstein's model, which simply predicts the uh, uh, the the mean square value of position of these particles uh, is directly proportional to the time. Whereas Langevin's theory, which is more general, we'll see how it is more general. So it basically considers that the molecular collisions play a role in defining the type of motion these particles have. So we assume that the molecular motion collisions are random. They exert random force on these particles, and let's say we denote this force by capital X, which will be a function of time, because we don't know at which collision what type of force will be acting. Of course, this will be vector, and let's say a particle has a mass of small m, and then this v is the velocity due to this force x of t. So it will also be dependent on time. So so we have this unbalanced force, so we don't know what basically the direction of this force is and what is the magnitude of this force is, but it is a random force. Okay, so if we have this force, we can write the equation of motion by using simple Newton's law, and it tells us that the change in the acceleration will be basically because of this force. Now this force can be expressed in terms of two, like roughly we can express it as two quantities, like combination or resultant of two forces. One force is because of a driving force, okay, that is because of the collisions, and another force is the opposing force. So this is you're having some force in this direction, but there will be some opposing force because of the viscosity of the medium. Okay, and that is given by beta times mv, and that viscous force or viscous drag also depends on how fast the particle is moving. So therefore it is dependent on velocity. It's like when you drive your bike, and there will be air drag which will be resisting your motion, your and bike's motion, and if you try to drive faster, you will experience the drag being faster. So same thing the particles also exhibit. They also experience the similar type of force when they are moving in the fluid. So this is the kind of balance known force. However, this is again this part is your fluctuating force, because of this unbalanced force, which is mainly due to the collisions of these particles with each other. So the viscous force can also be written by using Stokes' law, which assumes that it is a spherical particle experiencing a drag, and that comes up to be 6 pi eta rv, where eta is your viscosity, and then 6 pi eta we have simply beta for that. So that's what that's the another way of writing the viscous drag force. Of course it has minus sign because its force is acting in opposite direction to that of the motion of the particles. So simply now x of t is having two quantities in it, so therefore we write the equation of motion slightly better way, and this quantity, this unbalanced force, is random force, so therefore on an average it will be 0. So if you take the net force over the entire ensemble, that means acting on all the particles at all instants, at all positions, that average will come out to be 0. It's a fair assumption because you have random things average out to be 0. So if we take the average on this equation of motion, the ensemble average, then this average velocity, we can write this equation of motion just in terms of averages. So average force is 0, that we already know, so we just simply have the motion due to the drag force on an average. Okay, remember this is an average force, or this is the equation of motion for the average ensemble average. Okay, at any instant you will always have this force, but on an average the force will have 0 value on an average over the entire ensemble of particles. Now we can simply solve this because this is simple equation, simple differential equation. So you have dv by v here, m can be cancelled, minus beta times dt. Now you can integrate, so you'll get ln of v minus beta t, and if you take out ln it will be v equal to and substitute that integral from 0 to t, you will get v of t equal to v of 0 exponential of minus beta t. Now this beta is now we have another symbol for 1 upon beta, that is tau c, and tau c is called as relaxation time because it will have the reciprocal of time, the units of reciprocal of time, the beta. Therefore 1 upon beta is tau c, and that is called relaxation. So it will be the time, average time between two successive collisions. And let's say we have this force f of t is as a next step. Let's say we know that f of t is some mass times the new quantity a. Just because we have mass here, and if we have expressed this force in terms of mass and some another quantity, then we can get rid of m from everywhere. That is the sole purpose of describing f as a times mass, and therefore this will be the new equation. So this is the I should have actually put average here. So this is the average velocity expression. Now if you take this f equal to ma, and then m goes out from all the quantities, then you will have the new equation of motion in terms of a. So here now we express the v as the first derivative of position, where x is, now we are introducing x as a position. So x dot stands for velocity, and second derivative of x, that is velocity's derivative, that is your acceleration. So your acceleration is x double dot. X double dot here it is simply v, so therefore it is only x dot, and we are multiplying x on both the sides. So x double dot equal to minus beta x dot plus xa. So this is simply this equation in terms of short draw notations in terms of x dot and x double dot, which is x dot is simply v and x double dot is acceleration dv by dt. Now we can do little bit of algebra here, and which gives you the expressions for x double dot and x dot. Okay, so you can do this, you can try this. If you take the derivative of second derivative of x square, you can express this x double dot and x dot. So if we can use this, and we get everything in terms of now x square and x dot square. Okay, so with this again, since we know that average of force, this unbalanced force over the entire ensemble is 0, we can assume fairly that this quantity, this xat, is also on an average 0, but this is a time average. So, and if you remember your initial part of statistical mechanics, so in general we assume that the ensemble average and time average are the same. So therefore this is fair assumption that x times a of t is also average of that quantity is also 0. So if we do that, we can get rid of this quantity here. So we simply have this equation, and therefore this, so we can express now the average of x dot square. So we are trying to get an expression for x square average, mean square average, which we, if you remember, we did that for the Einstein's model of diffusion. So if you see, Einstein has assumed that the particles are diffusing through the fluid. Here we are actually considering the molecular collisions. Okay, so that is the difference, and this is more general because we are considering more phenomena exhibited by these moving particles. So one more assumption comes in here. The assumption is, if you remember the equipartition theorem, you know, the each degree of freedom which is if the energy in that degree of freedom is expressed in terms of the square of the variable, then you get the energy coming from that, or the contribution of that degree of freedom to the total energy is half kBt. That's your equipartition's theorem. So just remember, we have here half kBt we can express for this x squares and then x dot squares. So we express that for x dot square from equipartition theorem, and so that gives you this 2 kBt upon this, because we don't have m multiplied, so we have taken it as in the denominator. So again we can now we have this equation in terms of x square, second derivative and first derivative of x square average equal to twice kBt by m. So let's say that this is m, this is y, sorry, this is y, so this is y here, and then of course this is so I think there is a mistake here. So d by dt is equal, d by dt of x square average is equal to y, and therefore this quantity, second derivative of x square average, is dy by dt. So therefore this is y, so it should be dy by dt of x square average equal to y. So that gives you this equation, and you can simplify this, dy by dt equal to minus beta, and if you integrate this you will get an expression of this type. So y is now some twice kBt upon m, so c more or less it is constant at constant temperature, plus this exponential of t minus t by tc, and because you can see here you have two quantities here, so you can take this dt on this side and then this y here, and then you will get expressions like exponent the dy by y kind of expression here, and then you can take dt here, and therefore you will get the exponential type of integration. After integration you will get the exponential terms in there. So in this equation at time t equal to 0, we can substitute t equal to 0, that means this is 0, so you will get y equal to simply this quantity, sorry, y will also be equal to 0 at t equal to 0, because at t equal to 0 there is no spread of these quantities, and there will be no change with time also. So therefore, because y is defined as d by dt of x square, that is equal to 0, therefore, and this quantity is coming out to be 1, so c is equal to this quantity. That's what we were trying to find out. So we substitute that c is equal to that, so that comes out, and therefore this y is equal to this coming out, this quantity coming out of this bracket. From these two quantities we have c is equal to this, and therefore we just have 1 minus e to the power t upon tc. And if you again integrate with respect to time, now you have to integrate it twice with respect to time, so you will get x square on this type of expression. Okay, it's not that difficult, you can work it out. So you get an expression for x square here, which is like not so simple as we expected in diffusion model. In diffusion model you had simply x square average as constant times t. Okay, here instead it is having a term having t there, but also you have exponential part. So so it's not that simple as Einstein thought. Then you have we can have special cases like at very small time t. Let's say we just started our Brownian motion, then what will happen? So if t is very small, you will see that if t is very smaller than tc, this quantity becomes very small quantity, e to the power minus x and my x is very small, so you can express the Taylor series expansion here. You can use the Taylor series expansion, which gives you the 1 since it is minus sign here, so 1 minus x, that is t upon tc, plus half t square upon tc square, tau c square. So and then you can neglect the higher order terms. So 1 minus, so 1 is gone, so 1 minus t by tau c, and there is already a minus sign here, so it will become plus, and then again minus. So t by tc here and t by tc of this second term will be cancelled, and then you simply have minus minus plus t square upon tau c square. So therefore tau c square will get cancelled, and you will have 2 kb t upon m time t square. Okay, here t square will come out, and this is nothing but, since x square is equal to some quantity time t square, so this has to be having dimensions of velocity. So this is x square v square, and this is nothing but the thermal velocity. Okay, so the particles will start moving in the beginning because of the thermal energy it has, and or you can say with thermal velocity, which is not told or which is not given by the Einstein's model. So it tells you that in the beginning it will change, it will vary as quadratic in time, t square, whereas Einstein tells that it will just change with t, it will be dependent on t, whereas here we have t square dependence in the when the t is very small. Now when t is very very large, so if t is very very large, you can neglect this quantity. If t is very very large, then you can neglect this quantity from here, and then you will simply have, this is t is large, so t upon tc, t upon tc will be very large quantity, and you can say that my infinity, so e to the power minus infinity will be 0, and therefore this is, and you can neglect 1 because t upon tc, so you can neglect this entire bracket. So it will simply have this quantity upon t upon tc, tau c 1 tau c will get cancelled, so you have this thermal velocity times tau times tau c times tau t, sorry. So this is the quantity for when t is very very large. And now here it is fine, Einstein model tells also the same thing, that the average value of position square, mean square of position, will depend on time. So this is fine when the t is very very large, but at t is very very small, you have t square dependence, time square dependence. So this is similar to your Einstein's model, and this actually gives you the expression for your diffusion coefficient in terms of this kbt upon m beta. If you compare this with your this relation with Einstein's model, and where you can express it in terms of b, where b is the mobility of the fluid. Alright, so with this we finish our Langevin's theory of Brownian motion. So advantage of Langevin's theory, that it can tell you what will be the situation in the beginning, okay, and it is more accurate than the diffusion model. Diffusion model tells what will happen, or predicts more accurately what will happen when t is very large, whereas Langevin's model can explain when t is small, and as well as when t is very large. Alright, thank you.